Hello, welcome back. Today I'd like to digress a little bit and talk about a very useful algorithm known as the expectation maximization, or the EM algorithm. Basically, the EM algorithm is just an algorithm for parameter estimation. For example, I have a random variable x here that is parameterized by some parameter theta. And my goal is that I observe some observation of x. I'm trying to estimate theta. So, just like it here. In many cases, that maybe I should hide this first. It's actually rather difficult to solve this problem directly, given just these samples x alone. But however, if I'm also given some latent variables z for each sample x, for example, if I'm given not just x1, x2, not just having a samples x1, x2, and so on up to xn, but I also have some latent variables z1, z2, and so on to zn, it would be much easier to get an estimate of theta. So a classic example for that is the mixture of Gaussian model. So like this here, I have x, basically a mixture of 3 Gaussians with different means and different variances. And let's say I have probability P1 to get samples of the first Gaussian and P2 from the second Gaussian and so on. Like this sampling points here. So I just highlight that like one color when I'm getting sampling points from one distribution. So if I know that the points, the corresponding kind of membership of the points, that is like which distribution that actually generate the point, then it's quite a bit easy to estimate those parameters. Basically in this case the mu and sigma square, the means and variances, by simply computing the empirical means and empirical variances of the corresponding data points for a distribution. For the corresponding distributions. And however, if I don't know the membership, then it'll be difficult. So in that case, Z here is basically just the membership of this data point here. So EM is basically just an iterative algorithm that have 2 steps. One step is trying to find the membership. That's basically this latent variable kind of, or like actually the probability, the a posterior probability of the latent variable given the observation, and then based on this probability and the observation, I'm trying to estimate theta, and this procedure will be repeated iteratively. Okay, let's start with this derivation. This derivation is kind of different, I think, from some other derivations, maybe more popular derivations from the web. And I think this is, I don't actually remember the source of this derivation. I think I read it from some tutorial paper, but unfortunately, at that time I jotted down the notes and I forgot to mark down the reference. So now I don't exactly remember where I got this from, but this is definitely not from me originally. So anyway, recall that, okay, what we are going to do here is we're trying to estimate x given theta, estimate theta given x, some observation of x. So if I do a maximum likelihood estimation, basically I'm just trying to maximize P given theta, the likelihood given theta, and then with respect to theta. And It'll be the same as trying to maximize the log likelihood instead, the log probability P is given theta. And then I can try to rewrite the probability as sum of some joint probability P is Z given theta. So basically this marginal probability is just sum of this probability here, conditional probability here. And then I can add a conditional probability QC given X. It doesn't change anything. I add that in both numerator and denominator. But if after adding that, know that this is kind of like an expression of trying to compute an expectation with some probability given like QC given X here. So even though this is a conditional probability, you can simply think of this as just a any other probability function that is a PMF. So therefore, log function here is concave. Therefore, like by Jensen's inequality that we showed last time, that this expression will also always be bigger than this expression here, because this is more or less like the first one is like f expectation of x, where f is a concave function, will be always bigger than equal to the expectation of fx here, as long as f is concave. Okay, note that last time we actually show an expression that is with a sign that is flipped, but in that case last time we actually discussing like f as convex. So now when f is concave, basically it's just the inequality sign is just flipped. So okay, then we basically have something like this. So this is the problem we're trying to solve, and we'll call this objective function as a fq theta here. So basically, EM algorithm is nothing but just an iterative algorithm trying to alternatively maximize this argument Q and theta alternatively. Thus, we have two steps. One step is trying to maximize fq theta with, let's say, theta is constant. I'm trying to maximize Q. So therefore, we can think of like this the Q in the next iteration Qt plus 1 is equal to, okay, will be basically trying to, with the last theta is fixed, I'm trying to maximize over Q, and then we're trying to maximize for the next iteration to get the update of the theta as trying to maximize theta. So sorry, trying to maximize fq theta of fqt theta with qt as fixed obtained from the last iteration. So that's basically just it. Let's see, maybe I should write like this, yeah. Actually, it turns out that this will be the maximization step, the M step, and this will be the E step. Okay, let's start with the E step first. So I can write this fq theta. Okay, fq theta is given by this guy here, right? I can write this fq theta as this here by basically expanding this joint given probability px and z given theta as pc given ps given theta multiplied by pz given x theta, and then I can expand that, basically just expand into two terms. So I group these two terms in one on the first term, and then px theta in the second term. So note that what happens is like this x theta, px given theta is here is does not depend on z. So therefore this can pull it out, and my sum over q here basically this will just give us 1 here because q is a PMF here. So therefore this is just equal to log px given theta. And for the first term, basically I will just flip the numerator and denominator here and put a minus sign here. But if I do that, then basically this is nothing but, as you can see, it's just the KL divergence between Q and P. Basically, more precisely, it should be the minus KL divergence between Q and P. And so, therefore, maximizing FQ theta is equal to maximizing this here. Now, if I try to maximize over Q, the second term doesn't have anything with respect to Q. So basically, it's just a constant. I can ignore it. And for the first term, it's maximized. Okay. And for the first term, it's maximized only when Q is equal to P, right? Because D is the KL divergence, as we've shown in previous videos, that D has to be bigger than or equal to 0. Maximizing minus D will be the same as trying to minimizing D will basically force us to have Q equal to P. So therefore the optimum Q is just equal to PC given x theta. So that's very simple. Okay, now let's look at the M step. Basically the M step is trying to maximize FQ theta with respect to theta, as we discussed just now. And we just copy this FQ theta here now. FQ theta is given by this. And instead of like in the E step, we're trying to expand like Px on Z given theta. We're trying to just expand this log here, so into these two terms here. Note that in the second terms, it's essentially just the entropy function of Q. But what's more important is that this function has nothing to do with theta. So therefore, if we are trying to just maximize with respect to theta, we can really ignore the second term. So therefore, we only have this instead. So, and that is our M step. So to summarize, we have the E step and M step as follow. In the t plus 1 iteration, the Qt plus 1 will be given by Pz given x theta t, and the M step theta t plus 1 is given by this expression here. So roughly speaking, the name on E step and M step is due to the fact that in the M step we are really computing the expected membership, as you can think of like in the Gaussian mixture model. The Z is the membership. So this is like computing the expected membership of given the observation X and also the current parameter estimate and current estimated parameters. And in the M step, we're trying to maximize the objective function and find the estimated parameter based on the expected membership that we obtain in the E step, and also the observation X. Okay, that's a summary of the EM algorithm here, and it's like what I want to talk about for EM algorithm for now. In the next segment, I probably will try to give an example, a concrete example of EM algorithm for Gaussian mixture model. Okay, thank you.